Good. Yeah. Final talk. Good afternoon, everybody who's still here. So let's talk about databases. I guess everybody knows me already. Michael and me, we're from Vienna, city of fatty foods, classical architecture, and beautiful women. So like I always introduce us, or at least me. I'm not sure if you're totally fine with that, but yeah. No, don't adopt it. I once had somebody complained that this is probably against the code of conduct. I'm still not sure, because it's again you're making fun of the appearance of somebody, even though like just clarification, like everybody loves her, and it's just like we're kind of proud, and yeah, it's not discrimination. Yeah, whatever. I'm still working at Elastic, infrastructure, pipe, developer advocacy. If anybody wants stickers, yeah, grab some. I have more than enough. And yeah, I run my database meetup and my papers meetup, and this is kind of the combination of these two things. So at beginning, we'll start off with some of the classical papers. How did we get to databases like they are today? And what's the current trend and going on, and why should you use stuff and why shouldn't you use stuff? And we'll just pick some common tools and see some use cases for which they might be a good fit. Okay, so let's jump into the databases. Yeah, the original paper, 1970, a relational model of data for large shared data banks. I always find this data bank writing interesting. Anyhow, written by Cod at IBM Research Lab, and he just had this idea like before that. Yeah, I'm back. Cool. It's blinking. Yeah, but doesn't the blinking mean it will go? Yeah, nevertheless, you can hear me anyway. Like. Okay, then for the recording. So Cod had his paper, and like before he wrote his paper, there were databases. They used slightly different approaches, like you had those network databases, but these implementations were super specific. So if you started writing your application against one of these previous databases, you really had to know how they actually store data to access it efficiently and to write data efficiently. So you A, had to know the system, and B, it was super tightly coupled to the actual implementation. And then Cod said, like, this is not a great idea. I'm just creating a generic model. Everybody will stick to that model. And then you have some system where you can, you don't need to care for the internals. And also you can probably simply switch to different products if you don't have to have this like low-level integration. And what he actually created was just a mathematical, a mathematical model called relational model and normal form, which kind of guaranteed this data independence, that you don't really need to care for the internals of the data store, but actually the database takes care of that. And what he actually created was this line up here. And what we are now using is the SQL statement at the bottom down here. So we're basically selecting the name from all the people who have not yet died. But what is actually happening behind the scenes is like you have a free variable t with an attribute name, and there exists a tuple with name and died at age. And there is, in that tuple, there is, it is of people, and there is died at age is empty, and the name of that died at age and the name of that free variable from the beginning, those match. And this is what Cod actually defined. So it's just the mathematical model. He didn't touch the SQL part. He just created a system behind it, like how does this work in the background actually? What is the theory? And then also IBM created another paper, SQL, a structured English query language. You can see SQL was spelled differently back then because of some trademark issues. And I think that the company that had held the trademark on that is long gone. But because of the issues, they simply removed a few letters and came down to SQL. And one fun fact about that is like IBM was really driving the databases back then, and also you had COD there, you had SQL. There is also a very nice long text, like it's 60 pages or something, where all the researchers from IBM met, like I think 10 or 15 years after their creations, and just like discussed how stuff happened and how stuff developed over time and how they got there. And one funny anecdote is that back at IBM you could tell everybody whatever you were doing because nobody got anything done anyway. It's probably pretty much the same at IBM today still. And some external guy called them and asked for lots of implementation details of their System R database back then. And they thought, well, it's probably the same. We'll just tell him, and he can do whatever he wants because nothing will happen out of that anyway. And I think they gave him pretty much all the details he wanted, just not the error codes. And that guy turned out to be Larry Ellison. And he just got like all the stuff the IBM guys had been working on. And he's the only one who got really rich based on that. And I'm sure the others are not badly off, but like they're by far not as rich as Larry. Yeah. So what you actually get then from SQL and the relation model is you have the declarative form. So you don't really need to care about all the details of your database system. That is part of the query optimizer. You don't care how the data is actually stored and synced to disk and how the querying process behind the scene works. You just have your SQL, and whatever happens efficiently in the background, but this is kind of none of your business. And you can also see SQL back then has been created for user interaction because it was so simple, even somebody who was not trained with IT systems could actually use it. So you can write these aggregated reports in just a few lines of SQL code, which was deemed super simple in comparison to everything that has been there before. You could gather powerful reports, but these untrained users, and probably also the trained users, don't want to take care of stuff like concurrency, integrity. So all of these features are in the SQL or relational databases as we know them. But also like this was kind of for development. Like the NoSQL world we know today, they didn't have lots of features in the beginning. And now all of them are adding more and more features because users demand them, like some sort of query language. And it was pretty much the same for the relational world. Like in the beginning, those products were super simple, and then they added more and more features until they are what we know now. And now we have a pretty good idea what relational databases actually are, and even though we have these minor implementation differences between them, the general concepts between different products are very much the same. Also because COD did another thing, he wrote a paper called COD's 12 rules, which are actually 13 because like every good person in IT, he started counting at 0 and they went down to 12. And there he defined what a system needs actually to do to be called a relational database system. Because even back then you had people riding the buzzword train, and people just had some older database implementation and they would just put on some minor things that he had defined in his paper and then call it a relational database because that was the cool thing back then. And he then actually defined his 13 rules where he said like, to be actually a relational database, you need to follow these rules and do these things. And thanks to that, or at least partly thanks to that, like relational databases are very much what we know today, and they are pretty much one concept. And unlike the NoSQL world, where everybody is kind of doing their own thing at their own pace and there are no standards at all, the relational world has held together pretty well, and all the products are kind of comparable. Yeah, and even back then people started writing their relational databases. Now this time is nearly over now, that people just start writing their own NoSQL implementations, but at some point, like 5 years ago or so, you had the feeling that everybody who was a bit bored sitting at home started writing their own database. But for many people, it probably was not the best idea. So if you have no idea, like Dilbert's boss, don't try to write a database system. Yeah. And then we kind of fell from a variety of databases, somewhere, I don't know, in the late 80s, early 90s, whatever, from a wide variety of databases into a dark age where the market was kind of concentrated, and it looked something like this. And there were just a few big players, and there was not that much innovation anymore. Like the big players bought up the smaller ones, and yeah, they had their systems, which were sold at often very high prices, and people were just using them, and that's it. No big innovation at that time. And Uncle Bob, who's also pretty well known in the Java circles, he has a very nice blog post where he describes or compares this with the prohibition in the US in the 30s, or was it the 20s? Whatever, where they were not allowed to brew beer. And he says, like, kind of the same thing happened in the database world, because like in the US, they kind of forgot how to brew proper beer. That's why their beer was so tasteless and crappy for a long time. And the same thing happened to databases. Like, people lost the knowledge actually how to create databases. And only in the 2000s it was kind of rediscovered, and like we have all these microbreweries now and everybody is brewing beer again. The same thing happened kind of to databases. Yeah. And what was driving this need for new database systems were two things. First off, relational databases were often perceived as slow and inflexible. And you can think of like the dog as your application. And obviously your application would be much faster on its own. But it's sitting on the slow turtle. And turtle is slow and inflexible, just like the relational databases. And people had the feeling like relational databases are like this turtle. They're just holding me back and I cannot really do what I want to do. So they were looking for ways to break free. And the only thing that's kind of working against you, no worries, this is the last paper, is the famous CAP theorem, consistent, available and partition tolerant web services, even though it doesn't only apply to web services but any distributed system. Who is actually familiar with the CAP theorem? Who is not familiar with the CAP theorem? Okay, I assume the rest are sleeping. No, but we had nearly everybody was still awake. Okay, just to quickly jump into that, you have 3 attributes and you want to have all of them. First off, consistency. Consistency is you have multiple nodes and you can query each one of them, and at one point in time you want that all your systems give you the same answer to a specific question. Like consistent view in time, that all systems agree on what is, I don't know, your current account balance or whatever information. This is obviously something you want. Like different systems giving you different answers is probably very confusing. Secondly, availability. You want all the nodes in your system, every node that is actually reachable and available, you want that node to be able to respond to your queries and not just say, nah, my cluster is in a bad state or something, cannot help you at the moment. You actually want all systems to interact with you. And the third thing is, if you have a distributed system, partition tolerances are kind of a given. Like bad stuff can happen. Networks can fail. You can have a long stop-the-world garbage collection. You don't know if the application is up or down. So you just have to expect the unexpected in your network. And this partition tolerance is something every distributed system will bring to you. And of these 3 attributes, you can at most pick 2. Like if you have a bad implementation, you probably only get 1 attribute or none of the attributes at all in some situations. But you need to choose, like, where do you want to be? You can either be here, here, or here, but never in the middle. Like, there is no way to get all of them. And like the paper describes it very, very nicely. Assume you have a distributed system, so partition tolerance is kind of a given, and you have 2 nodes on one side and 1 node on the other side. And then your system needs to decide, how do I interact when I don't see all 3 nodes at once, but like I have the 2 on the one side and 1 on the other side. And if one of your applications writes, for example, to the 2 nodes on the one side, you have your data written, that's fine. And then if a client reads data from the other side, how does that client react? And that is kind of the decision you need to make. Either it says, I cannot see the other 2, I don't know what is going on there, I don't respond, then you're not available. But you're consistent because you don't give out stale data. Or the other approach would be that the single node on the other side says, oh, I cannot see the others, but I will still respond to your query. I just give you the best information I have, but it might be outdated. So then you're available, but you're not actually consistent. And if you have kids, there's a very nice story. You can compare it to Robinson Crusoe. So Robinson Crusoe is sitting on his lone island. He's kind of partitioned from the rest of the world. And I think he was English, so if a ship comes by, or whenever a ship comes by, somebody might ask him a current question. like, who is the king of England? And since he is partitioned from the rest of the world, he then needs to decide, am I consistent or am I available? If he's consistent, he doesn't answer because he has not the latest news. Or he is available, then he answers, but he's probably not consistent with the rest of the world just because the news didn't get to him. And kind of the same applies to the CAP theorem if you have a distributed system. And there is this thing, eventual consistency, where data will eventually reach all the nodes and everybody will be updated. You can kind of compare this with a message in a bottle. And every few weeks he finds a newspaper or whatever in a bottle. And then he's kind of up to date until that point, and that is eventual consistency then. And some people will then say, like, my network is so reliable, we don't have these network partitions. Like, it just doesn't happen. There is this guy called Kyle Kingsbury, Twitter handle and domain Aphir. He's by now destroying databases on a professional level or torturing them or whatever. And he's also written a very nice blog post where he's like gathering all the evidence like that your network is probably not all that great. Like maybe you don't observe it, or maybe you have been lucky so far, but you just have to expect that bad stuff will happen. And he has this experience of Amazon and Microsoft and Google, and he says, I don't know, they lose that many routers and racks and even whole data centers over a given time span. And you just should not claim that you're that much better than these companies because they really know what they're doing. So it's probably your network will also screw up at some point in time. Okay, like that was kind of one of the pieces. And the other piece is schema flexibility. Many people started to say, yeah, relational databases are very nice, but like my application is developed in an agile fashion, and we just need to do stuff quickly. And this rigid schema is not really helping me. And for example, if you have used MySQL in the past, if you have any change to the structure, so if you have an alter statement where you add a column, for example, this will lock your table for both reading and writing until the operation is finished. If you just have a few megabytes of data, it will be very quick. If you have gigabytes and gigabytes of data in the table, this operation can probably take hours. And during that time span, your application cannot query that table, which is not acceptable for many systems. So people look for alternatives.
What about other database vendors on this problem?
I think Postgres is better. They didn't have this maybe writing. I'm not sure. Like I think reading is at least possible in Postgres. I'm not sure about the proprietary ones, but like the schema, of course, has some kind of cost. Like most systems actually have some kind of schema, but you don't duplicate it because normally you have the schema in your application, and you also have it in your database. And of course, you can keep those two in sync with, I don't know, Flyway or whatever tool you're using. But there's always this overhead that you have your application and the database, and you kind of need to bring those to the same state. And it just adds more problems that like, oh, you had a bad deploy, you've added some columns, and now your application expects those columns, and you need to roll back. Oh, can I roll back all my database changes as well, and have we tested that? And just stuff like that, this schema does often not really fit that well with the rest of your application. The full table lock in MySQL, I mean, there are now tools around it, and I think GitHub just has 1 month ago or so published again another tool how they do it. But at least in the MySQL world, this is still a big problem. And also for the others, like schema changes are not all that easy, and stuff can go wrong, and stuff takes time, and yeah. But for example, in Postgres, instead of that, you have probably the auto-vacuum problem or the vacuum problem, where you vacuum the database, which might be very heavy and where you need to do that for some internal cleanup and stuff. So, like, there's always some cost to pay. Okay, so what can you do? First, model would be, I don't have any structure at all, which is not, or doesn't make any sense for a database. Because like, okay, it's just Python, I cannot do anything with that. Next kind of structure would be key value. So you have a key and a value, and in a relational database, you're used to it that whatever you have stored in the database, you can actually query it. If you don't have an index, the query might be very slow, but you can still query it and you can always query. Whereas in key value store, you don't have the possibility anymore. You can only query over keys. What is in the value is just a value. There is no way, even if you know a part of something that's in a value, or even if you know the entire value, you cannot get to that in any fashion. It's just you only can do stuff over the key. Second one is, or the second useful data structure is, yeah, you might call them the advanced data structures. For example, the graph databases, they are very good if you have two nodes and they're kind of connected with some edges, and then you want to find the shortest path between two nodes. For example here, I mean here it's trivial because we don't have that many nodes, but if you have thousands of nodes and lots of connections between them, finding the shortest path between two nodes is like a hard task for relational databases. Then we have the document stores, I guess because JSON is everywhere and we all have our JSON data which we're sending around over the internet already. It's super popular just to store JSON somewhere. And you can also have richer data structures, like you can have arrays or sub-documents, and you can just structure your data in a nicer fashion, or more like, we'll see later how this actually fits with object orientation better. And then you have column family or column-oriented databases, where you don't only have this two-dimensional structure like you're used to in relational databases, where you have a column and a row, but there normally you have kind of a third dimension where you have time-stamped values, and you can then group those rows together, columns together, and it's also very efficient to just query specific columns and not rows. Whereas relational databases are super good in just fetching rows, like give me that row, give me that row, give me that row. But if you just want a single column and that's of lots of rows, that is not what relational databases are good at. This is what column-oriented databases are better at. And then you have the relational databases still, of course. And what you already can see here, stuff like relations and with that joins, that is in most systems only available in relational databases. I mean, the NoSQL world tries to add that, like with some constraints or not at all or whatever. But like to really have this rigid structure and then rich joins, this is normally the area of relational databases. Okay, and like this need for speed and the schema flexibility, these two led to the NoSQL world, which is not only SQL, but some people say actually it's called because of that. At some point you had a recruiter, and the recruiter asked you, like, are you an expert in SQL? And you say no. And then the recruiter says, we need to write something on your resume, so we will just write expert in NoSQL. And this is not how it happened. Like, there was I think some Italian guy wrote a system that was relational in the back end, but didn't expose an SQL interface, and that's why he called it NoSQL. The product is long gone, and then somebody picked it up as a Twitter hashtag when all these new fancy databases did the first conference or something. Like, I think it was back then Cassandra and MongoDB and probably HBase and one or two others. They did the first conferences on like all these new database trends, like the microbreweries, like all the people writing databases now, they got together to discuss something and they needed a short hashtag, and they settled for this NoSQL, which is probably not the right term because no rel for no relationship might be better. Or now that many products are starting to add SQL-like query interfaces, it's kind of funny to have them in the NoSQL space, but actually to support SQL or a subset of SQL. Yeah. And then the other thing that often comes up is like, how does this actually compare to big data? Yeah, because probably your boss wants to do big data because it might make you lots of money. And like Dilbert's boss says, the book of Wikipedia says, I don't know how much data there is, and this will make you rich. Yeah, and of course it lives in the cloud and all the usual stuff. So there are generally two definitions of big data, just to quickly cover that as well. One of them is very broad. It's just like very big data sets, probably stuff you cannot fit on a single machine might qualify as big data. And the other definition is like a bit more specific. It's more about offline data, and you have these data warehouses like Hadoop and Spark, where you just do some processing, and it doesn't need to be online and real time. It's just like some job in the background that's probably getting some new insights from all the data you have, and extracts that. But like many other people, I think that big data is kind of overrated, and that it's just a term that's thrown around all the time, and people, yeah, just use it because it sounds very fancy, and everybody thinks they will get rich because of it. Okay, and then there is DB Engines rank, where you can actually see which databases are popular. I mean, I'm not sure how well defined their metrics are or how good they are, but yeah, they have a ranking, and we'll just pick a few open source tools we take a look at. So we take a look at Postgres, that is super popular at the moment, Mongo, since it's the most widely used NoSQL database, Cassandra, Redis, and Elasticsearch. And we'll just go quickly through one use case for each of them to see what they're good at and what they're not good at. So MongoDB, but what I say about MongoDB pretty much applies to everything that is a data store, a document store. So it might be CouchDB, Couchbase, Elasticsearch, whatever stores your documents. This is pretty much the same approach or idea. This is just MongoDB is the most popular one, so we'll take that one. So it stores JSON. Yeah, that's not a big surprise. And the aspect I want to cover is like there's this famous quote from Ted Neward, ORM is the Vietnam of computer science, which was written like 10 years ago by now, I think, and Hibernate had just started, and ORMs back then were pretty terrible. Depending on how you view them, they are still today. And he was just like, yeah, we have this impedance mismatch, like we have relations on one side and objects on the other side, and these two just don't go that well together. And this is not pretty. So maybe documents work better. Yeah, actually, why is there this impedance mismatch? Who has actually written something like that already in JPA, Hibernate, whatever? It's an end-to-end join, I think, which you can traverse from both sides. So, who thinks this is okay? No? Yeah, no. Yeah, it's like saying, yeah, I'm okay, which is either the Stockholm Syndrome or you're still in denial. Yeah, let's just take a quick example. So we have an abstract base class, employee, and then we have managers who can approve funds, and we have workers who have experience. Obviously, managers don't have any meaningful experience. And how could we implement that with a relational database? There are 3 approaches, and none of them is really great. Like, the first thing you might want to do in a relational database is just have a union table, probably with many null values. So if you have just 2 specific implementations, it's not that bad, and each one of them had just 1 attribute, so it's fine. But if you have more implementations and lots of attributes, you don't have really a rigid schema anymore, because you have mostly null values, and you cannot really enforce any not null constraints, because nulls are everywhere. It just isn't really made for that. You don't really have a schema, you have more of a Swiss cheese where you just put in bits and pieces of information, but you can see in the object-oriented world it just fits very nicely, and then your relations are kind of bloated and don't work that well. So yeah, not a great solution. The other option would be a concrete instance. So you just create a table for your managers and one for your workers, and you can query them, and that kind of works. The only problem is, once you come to the point where you actually want to get the names of all your employees, managers and workers, yes, you can do it, but you need a union clause, and you need to join together your 2 tables. And again, like, this is pretty easy and elegant in object-oriented programming, but it just doesn't work that well in the relational world. Like, okay, yeah, you can put it together, but it's more effort, both for you to write it and for the database to always do it. So yeah, not so great. Third option would be you have, oops, so what's the wrong direction? You have a base table with joins to the concrete instances. So you have 1 table for employees, you have 1 table for managers, and 1 for workers. And whenever you want either a manager or a worker, you need to join that with the base table. Again, it works, but it is not as nice as it probably could be. So we'll take a quick look at how MongoDB does that. There is Morphia. They call it ODM, Object Document Mapping, because they don't have relations, so it's not an ORM, but an ODM. And we just add some simple annotations. Like we put all our documents in the collection, which is kind of a table employee. We have the same implementations of managers and workers. We just have an ID, but don't care too much about that ID here, which MongoDB uses for ID. And what you actually get in the database then is this. So you have one collection where you have all your documents inside. You don't have any null values because you can simply skip them. And if you want to query like the names of all the employees, it still works. So yeah, you even can, based on the class name, which is stored automatically, you can actually say, give me just the workers or give me just the managers. That still works. The only downside might be if you do lots of refactoring and want to move that package, you will need to refactor that as well with it. But in general, like this fits much better with the object-oriented world, where you just have your object, which map nicely to your documents. You don't have any joins, you don't have any null values. It's just like a better fit. No, that is automatically mapped through the class name. Yeah, but you will need, if you move your package or rename your class or something, you will need to refactor it as well. Or you could simply, if you know you will probably do that, you could simply get rid of that and use a custom enumeration. That's happening automatically. Like that's the drivers or the Morphia, the ODM is doing that for you. But you can disable it, and to make the differentiation, you could just create a custom enumeration. So MongoDB is super nice, or at least in my opinion, is very nice if you have just everything on a single server and then enable replication. But as soon as you need to shard your data, so you need to spread it out over multiple servers, stuff gets much more complicated. Because if you have everything on a single node, like this is where your data lives, and then you have the data replicated twice, just in case this node dies, you have two others who can actually take over the work and still have the data. But as soon as you need to split the data, for example, into 3 pieces because it's getting too large for one server or you have too many queries, this would be like these 3 pieces, then you need to replicate each piece. So you have 9 servers here. And then you have 3 configuration servers for production environments where you actually these just hold the state like which data lives on which of these 3 replica sets. And then you have another new component which is called a router, which normally sits on your application server, or you can also have them separately, which will actually talk. They get the information from the config servers where which data lives, and then they will just talk to the right server and get the data for you. So once you jump from single node that can hold your data to multiple nodes, you get lots of new components and stuff gets much more complicated. And also like MongoDB guys will of course tell you like this scales up to lots of data. I'm personally not really convinced that for really high loads or really a lot of data that this will scale that well. Okay, next up, Redis. Key value store and a bit more. Name comes from Remote Dictionary Service, which is kind of the omnipresent glue by now. Everybody is using Redis for something. I don't know, but Spring Sessions uses Redis automatically. But we're looking at a different use case. We will cover statistics, like you have a login and your marketing department wants to know who has logged into my site over the last hour. And you have 2 possible data structures to do that. Either you just store it in a BITSET, like the very first user that has ever signed up to your page is user 1, the second user is user 2, etc. And then you simply allocate 1 bit to each of your users. And if user 1 has logged in, you simply flip his bit to 1, and then you know he has logged in. So if you have 1 million users for that hour, just to track who has logged in, You need, I don't know, 120, 125 kilobytes of data approximately. Just one bit for each user. You simply flip that bit, and then you can actually see who has logged in during that hour. The other data structure that is very interesting is a HyperLogLog. HyperLogLogs can count unique elements like user IDs, IP addresses, stuff like that. And this is a probabilistic data structure, so it doesn't give you exact results, but it uses just a fixed amount of space. So it just needs 12 kilobytes, and it can store how many entries you have in that. And you have an error rate of less than 1%, so you can be pretty certain if you just query like, did this user log in during the last hour? You have a 99% chance that you get the right result out of that. And it uses much less space. And in general, HyperLogLog is very nice because it just has constant size and it uses a fancy data structure. BITSETs are nice because they're exact, and also they are super nice because you can aggregate them. Because after a week, maybe you don't care about the results for each week, but after a week, you just say, I want to know, has a user logged in during a specific day? And then you can just, the 24-hour slices you have, you simply OR aggregate them, and then you know, has this user logged in that time span or not? So overall, yeah, Redis is normally simply this omnipresent glue, but you probably don't want to write your entire application with it because like query capabilities are limited, but it's pretty fast. And the other drawback is it needs to keep lots of stuff in memory. Like the keys need to be in memory, otherwise it's not working. The values should be in memory, otherwise it's getting really slow. Okay, then there's Cassandra. What I find nice about Cassandra is that they are actually making fun of Oracle because of the name. Cassandra, I think she was in the Greek mythology. She was, I don't know, whatever she was, but I think she was one of the people living in the city of Troy, which was destroyed later on. And she actually saw the future. I think she saw that the horse would be something bad. And then some god sent some snakes or something to kill her. But at least she saw the future even though nobody believed her. Whereas the Oracle in Delphi, they didn't know anything. They just made stuff up and yeah, babbled over their fumes. So the Oracle doesn't have any idea, whereas Cassandra actually sees the future. That's why it's said that they picked the name. And nice thing is about Cassandra is it's very scalable and it's highly available. The thing it uses most is consistent hashing, and we'll just take a quick look at how this works behind the scenes. Yeah, this is a bit small. We'll just jump into each of these elements. So first off, you just have your key space. Every entry you want to store in Cassandra, you need to give it an ID. And then you hash that ID. Why do you hash it? Because you want to avoid hotspots. Otherwise, if you would just choose the keys yourself, you might, for example, if you would just use the last name of people, this is probably not really well spread out over the alphabet, and you would have specific hotspots on your service. And you want to avoid that, so you simply hash your keys. So if you pick a good hash function, which I hope they did, your data should be very evenly spread. And then you just slice your data. Assume you have 3 servers. You simply slice your key space into 3 equal pieces. And then, depending on where the hash, what the hash results in, that will determine the server where the data will go. And then you turn the whole thing clockwise. So again, we're hashing our data. It lands on server A. If you hash Y, it lands on server B. And just to keep the data multiple times, you then say, okay, initially the data landed on server A, but we also replicate the data. This is why this is clockwise turning. It's just the next server, if you turn it clockwise, gets the data as well. Like, this is not related to the network structure. These servers are not formed like a token ring network or anything. This is just like a logical order, like this is the ring and they're sitting on this position on the ring. And so the data will go to that node and then will be replicated to the next node. And then if you remove your server or one of your servers dies, okay, the data went here. The replication is gone now, or no, actually the B server is gone. So actually the whole data now falls onto the C node, since that node still had the replication, you can see here, we had hashed our value. It went to B originally and was replicated to C. Once B is gone, C still has the data, and then it knows, okay, I'm the only one who has that data. I need to replicate it to the next node again, and that happens to be A. So data is then copied over to A as well. And if you want to add nodes, you simply split the key spaces and add nodes in that area. So that's very easy, just to add nodes and remove nodes. And normally what you do is you will split your data into smaller chunks, so you don't, if one of your server fails, you don't have the full key space just going to the next server, but so you have this spread evenly over all your servers. So you split stuff into smaller chunks and distribute them over all your servers. So if, I don't know, server A dies, both B and C have some data as the primary and can then replicate stuff to the other one. Yeah, and then some people say, this is all nice, but this is eventually consistent, and this is probably not what you want. You can work around that. You can write and read your data with a quorum. Normally you would read and write your data 3 times, but you always need to wait for all 3 operations to finish, so that adds quite a lot of overhead. So most people don't actually do that. But for some use cases, this is totally valid to have data that might not be entirely consistent, but it's highly available. And some people always need to make fun of stuff, and they say, yeah, we went to immediate inaccurate. Yeah, the nice thing of Cassandra is it scales up very nicely. I think, what was it? How many nodes does Apple now have? 100,000 or something? And they said something like they have 1 cluster with 1,000 nodes. And that works very well. I only think that scaling down or like having few nodes is not really the sweet spot of Cassandra. So this might also be one of their drawbacks. Okay, and then there's Postgres. This is probably too small for you to read, but I can like act it out. Like one of the guys says, like the relational database is much too slow. We need to find something else. I've made a battle plan for migration to NoSQL now, and it will take 3 months, and it's lots of work, but it will be worth it. And afterwards, everything is fast enough. And then the other guy says, wait, let me check. And then he checks and says, wait, you didn't add the right index. And I've set the index now. The query is 100 times faster. All good. We don't need actually to migrate to the NoSQL world. Which is probably true for many use cases that they still fit onto a single relational database. And actually by now they're often called SQL databases and not relational databases, since the SQL standard has evolved a bit further than just the relational model, what it provides. Yeah, and you could say this is not only RDBMS now. And the other thing is they are well tested and they support SQL. And everybody wants to write SQL queries. So now lots of people started to write their own implementations. Some are pretty close, some are pretty far from what the SQL standard actually does. Like Cassandra has the CQL, Couchbase is a bit more creative, it has Nickel. The others are, yeah, RethinkDB has 3QL, Google has GEQL, whatever. So they all try to replicate that. Which worked well for us. For some, Cassandra's query language is very different than what you would expect. Like it's just like in the beginning, first half hour, you think, oh, it's SQL, I know what I'm doing. But then it turns out it's behaving a bit differently in the background. And also the relational folks are normally super amused when they see this. Because what's the current standard that Nickel supports? 92? Okay. At least there's some of the NoSQL databases say, oh, we actually support the SQL 92 standard. And the relational guys then say, yes, this is like somebody boasting, I'm supporting Windows 3.1. But because it also came out in 92. And nobody would promote his product by saying, I'm Windows 3.1 compliant. But the NoSQL world does that. Yeah, so what you get is maturity, features, and you also get this NoSQL influence since, yeah, you have now JSON. In Postgres, MySQL will get JSON at some point in the future, or it's already there but not as usable yet. So yeah, more and more features. The dark ages are over. Everybody is kind of profiting from what the NoSQL world does and the relational world. So yeah, they're helping each other out. And then there is Elasticsearch for the full text search use case. Who was not in my talk yesterday? Okay, then I'll quickly go over that. So what makes full text search different is you actually want to search stuff. So you need to do some extra steps when you actually query or insert your data. So what you normally have, you have some text. What you want to do is you remove the formatting, because you don't need, for example, HTML tags, you don't care for them. You don't search for HTML tags, you just search for specific words. Then you parse it, which basically means you just find the different words. So you split them up on spaces and punctuation marks. Then you remove stop words. Stop words are very common words. You don't really want to search for them because they appear in every document anyway. It's like and, a, if, words like that. They would just add weight to your indexes, but they don't actually give you anything meaningful. Then you do stemming. Stemming basically means I remove the word ending because I don't care about singular or plural or even noun or adjective. I just cut the word down to its root and simply want to match on that. And optionally, you can add synonyms at the end. So what this would look like in a concrete example, you have 3 documents. You run them through, you've removed the formatting, there's no formatting here. You found the different words. You define the stop words, you remove them, and these are the words that remain. So you see, these are the terms I have extracted. And these are the documents where they occur. So if I want to say, give me all the documents where great occurs, then you can simply say, document 2. Or if you say, I want to get all the documents where blue sky appears, then you see blue appears in document 1 and 3, sky appears in document 2 and 3. So if I search for blue sky, I only get the document 3. And since you have extracted all these words, you can simply look that up in the list, simply connect, if you search for multiple terms, like which documents contain all of these words, and then you get back what you have searched for. And there's always this quality aspect. This is actually the formula, how you calculate that. We did that in depth yesterday. Yeah, time is more or less up. We'll skip that one. Yeah, and we have full tools that are around that for logs and analytics and stuff like that. So to conclude, depending on when you looked at databases, you had different views. So in the beginning, in the 70s, there was no SQL. Then in the 80s, it was suddenly, yeah, you should know SQL because this is the good thing and you want to use that. Then in the 2000s, again, it was, no, SQL, this is too slow, too inflexible, we don't want to use that at all. Then in 2005, it was not, okay, not only SQL, we had these SQL interfaces, but we have no SQL databases, and it's kind of getting all together. And then at some point, maybe that happened or didn't happen, depending on your point of view, people actually said, no, this whole NoSQL thing is crap. We should go back to SQL because actually this is what most applications really need and want. And then there's always a question like, but what is the fastest system? Is it fast? And I'm always showing this comic where somebody under similar conditions tests, is the squid more intelligent than the house cat or vice versa? And he then concludes like, obviously the squid is much more intelligent because the house cat is dead. And this also was very nicely illustrated, like I think it was 1 or 2 years ago, when Couchbase, MongoDB, and Cassandra did a benchmark, and each one of them managed to be at least twice as fast, because each one of them found some scenario where they were much faster. That's why most of these benchmarks, especially when they are made by a vendor, are total crap and don't tell you anything. Yeah. That's it basically. Grab some swag or find out which database you might want to use for your next project. This is already 3 years old. I think HBase is not so much in fashion anymore. FlogDB, I'm not even sure that's supported anymore. But other than that, you can see where you actually end up with your database needs. Thanks.